Hi guys, I encountered a lot of problems when I was looking for the development of vertebrate eye on YouTube. Well, unfortunately, couldn't really find an explanation, so I'm here to help myself out so that I don't have to go through the texting again and again, and a little understanding for you guys as well. Now, before you watch this video, I request you to watch a video entitled General Embryology Detailed Animation on Neurulation by Embryology. That will give you a fair idea of what we are talking about. So, to have a fair idea of what we will be talking about in the following slides, you need to watch general embryology detailed animation of neurulation to see the formation of neural crest, neural tube, and then just come back to this video. Okay, so I've made a rough neural tube here, and there are two parts of neural tube, that is anterior neural tube and the posterior neural tube. Anterior neural tube will give rise to brain, and posterior neural tube will give rise to the spinal cord, and there's a neural crest shown in green. And I hope from the video on developmental embryology you might have understood what the neural tube, neural crests are and how they are developed. So during initial neurogenesis, certain anterior neural tube region, that is anterior, as you can, I hope you can visualize now, certain anterior neural tube region cells start expressing noggin. Noggin is again a transcription factor, which initiates a cascading effect. Therefore, the formation of certain other transcription factors that are PAX6, PIX1, and RX1. Now, the expression of these transcription factors, that is PAX6, PIX3, and RX1, will lead to the development of eye field. Eye field, what is eye field? We will just discuss in the upcoming slides. Eye development involves three steps. First is the formation of eye field and optic vesicle. Second one is the formation of lens plecore, and the third one is the interaction between the two, that is optic vesicle and the lens plecore. The neural plate has to know the eye has to be formed here. So there's a signal, and what acts as a signal is the transcription factors, the expression of transcription factors 6, 3, PAX6, and RX1. The cells in which these three transcription factors express is the anterior tip of the neural plate. There, the eye field will start forming. The cells expressing these factors now develop the eye field. Eye field is nothing but the location where the eye will be developed. So, after the formation of eye field, the neural plate cells evaginate towards outside, and they form the optic vesicles. This single domain of eye field will later split into the bilateral regions that will form the optic vesicles, because we have two eyes. As you can see, the neural ectoderm, a part of neural ectoderm has started evaginating to form the optic vesicle. Evagination occurs due to the expression of PAX6, 6,3, and RX1 transcription factors. Once the optic vesicle has formed, it releases certain paracrine factors like bone morphogenetic protein 4 or BMP4 and FGF8, that is fibroblast growth factor F8, to the head ectoderm. Head ectoderm is nothing but the outer layer, as clearly visible in the figures. Now the entire ectoderm is incapable of responding to optic vesicle paracrine factors. Only some cells or a region of head ectoderm which expresses PAX6 would respond to optic vesicles. That is why we say that PAX6 develops competence in head ectodermal cells to respond to optic vesicles. PAX6 is very important. If there is no PAX6, there is no induction by optic vesicle. As simple as that and straightforward as that. Optic vesicle releases certain paracrine factors to head or cranial ectoderm. The head ectodermal cells with the expression of PAX6 will respond to the induction of optic vesicle, as we've already discussed in the previous slide. Well, a point to notice is PAX6 expression is very important in the head ectodermal cell for the induction by optic vesicle. If there is no PAX6, there is no induction, as simple as that. And people with homozygous condition for loss of function mutation PAX6 lack eyes altogether. So basically PAX6 is very important for development of lens and retina. Okay, now in response to BMP4 and FGF8, the head ectoderm produces SOX2 and LMAS, which are shown in green. SOX2 and PAX6 are responsible for initiation of lens differentiation, activation of crystalline gene, and the expression of LMAF gene is needed for maintenance of crystalline gene, expression and completion of lens fiber differentiation. Once the lens plecode has been formed, they both interact. Lens plecode and optic vesicle interact. Now lens plecode, initially optic vesicle induced lens plecode. Now there will be a reversal. Lens plecode will induce optic vesicle. This is termed as reciprocal induction. And optic vesicle now invaginates, as the figure B showed. Optic vesicle invaginates to develop bilayered structure. Basically two layers, an inner and an outer layer. Inner layer will give rise to retina and outer layer will give rise to pigmented layer and optic nerves. As previously discussed, the optic vesicle has induced lens plecode initially, and now the lens plecode will induce the optic vesicle. Now the optic vesicle, as seen in figure C, invaginates to form a bilayer structure. You can clearly see the two layers, that is inner layer which has been labeled prospective retina, that means it will form into retina, and the outer layer prospective pigmented epithelium is because the outer layer cells produce melanin pigment and become the pigmented retina. The inner layer cells proliferate rapidly and generate a variety of clear ganglion cells, interneurons, and light-sensitive photoreceptor neurons, which all of these cells collectively are called neural retina. Now in figure C, you've also seen that the lens plecode has completely invaginated and pinched itself off from the head ectoderm and formed the lens. And just above the lens, the head ectodermal cells have divided again and formed a complete layer, and this will give rise to cornea in the future. Therefore, it has been labeled as prospective cornea. And figure E shows a complete eye, which shows cornea, lens epithelium. Uh, Cornea and lens and eyelids are formed from the head ectoderm. The origin is head ectoderm, and apart from that, the retina, pigmented cells, iris, optic nerves, and ciliary body are developed from the neural tube. And one point to be noted is the mesoderm provides blood vessels and sclera, and there is no role, I repeat, there is no role of endoderm in the development of eye, since 90% of the eye develops from ectoderm and 10% of the eye develops from mesoderm. So as discussed in the previous slides, induction and competence will be discussed in the upcoming slides. So let's see what induction is. This is a very simple concept. Interaction between two or more cells or tissues of different history properties located close to each other is induction. Well, there are at least two components to every inductive interaction. First component, as you can see here, is the inducer, which changes the cellular behavior of the other tissue. Inducer produces signals that the responder takes up and responds to that signal. So responder is the tissue that is being induced. This is easy to remember and there is no rocket science to it. Then what is competence? The ability to respond to a specific inductive signal is competence. For example, PAX6 is a transcription factor which acts as a competent factor as well. Right? To sum up, you can just go through the points. The anterior portion of the neural tube forms the eye field, and then the optic vesicle, and in the bracket are the transcription factors, and then there's the division of eye field, due to which a single eye field develops into two eye fields because of sonic hedgehog, which is really important, and the absence of sonic hedgehog will lead to cyclopia, that is the single eye field and single eye. We would probably look like minions. Well, then head ectoderm forms lens plecode, and then induction of optic vesicle to lens plecode, and then reciprocal induction by lens plecode to optic vesicle, invagination of optic vesicle to form a bilayered structure, invagination of lens plecode to form lens, inner optic vesicle layer forms the retina, and outer optic vesicle layer forms the pigmented retina and optic nerves, and then there's the formation of cornea by head ectoderm. So I hope you understood the topic a little better. It took me a lot of time and efforts to simplify it down to this to these 11 slides, 11, 12 slides. And thanks to this wonderful book and its author, he has really made stuff easier for us. And since this was my first video, I hope you guys like it. And since it was my first video, so I'm pretty sure I might have made a lot of mistakes, so just point out if you find any and let me know in the comment section below. Thank you.